The planet Mars has long captured the imagination of scientists and the public alike. There have been more than 50 missions to Mars so far, and more are already planned for upcoming decades. In that way, in situ resource utilization, or ISRU, is crucial for the success of future space missions, and that is also the case for Mars exploration. ISRU refers to the use of resources that are available on the planet to support human exploration and settlement. On Mars, the atmosphere is very thin and is composed mainly of CO2 with a small percentage of other gases like argon and nitrogen. From an habitability perspective, this is, well, terrible. However, the abundant CO2 in the atmosphere can be converted into CO and O, which represent a source of important resources that can be used for a variety of purposes, such as producing oxygen for breathing and to produce fuels, which are essential to space missions. One question remains though: how can we dissociate the stable CO2 molecules? It can be done quite efficiently using a low-temperature plasma. First, we extract the CO2 from the atmosphere and then put it inside a tube or a reactor. By applying a discharge with an electric field that is high enough to ionize the gas molecules, the plasma is created. The electrons are then accelerated by the electric field and acquire very high energies and are capable of dissociating the CO2 molecules through collisions. However, the underlying plasma chemistry is a little bit more complex than this. We have to consider a lot of different kinetics, taking also into account the vibrational modes of the molecules. Even for a simple scheme, we have not only the electron collisions, but also the chemical reactions between the heavy species, where we might have to consider 2-body and 3-body collisions. On top of that, we can describe the reaction scheme with a set of rate coefficients, one for each reaction considered. The problem with this is that some of these constants are very difficult to determine and have a high uncertainty associated to them. This lack of knowledge is sometimes made up to some extent by the experience and intuition of an expert. Due to this required expertise and the time-consuming nature of this trial-and-error approach, it is of major relevance to find automated methods to determine these constants. So the question arises: can we use machine learning to determine these rate coefficients? And I pretend to answer that in my thesis. On a first step, I will be training a neural network from the simulated data of the plasma. To better visualize this, let's construct a neural network that can be perceived as a set of individual units called neurons, and that are connected to each other in the network. The neurons are organized in layers. We have the input layer, from which we can feed information to the network, the hidden layers, with an arbitrary number of neurons, and the output layer. In our case, we might want to give information to the network related to the properties of the plasma, such as the densities of the species. That information is then passed forward through the network, with the goal of obtaining the desired rate coefficients in the output. The challenge here consists of finding the right structure for the network and the optimization algorithm that best fits to the nature of our problem. And this is where my master thesis comes in. With the supervision of Professors Rodrigo Ventura and Vasco Guerra, and collaboration of PhD student Tiago Dias, I intend to find a model capable of predicting the rate coefficients of the plasma chemistry. Additionally, we want to investigate different methods to model uncertainties in the neural network, and explore the use of automated processes to identify the most relevant features in the reaction set, by eliminating minor species and less important elementary reactions.